This is STEM 101, Exploring STEM Technology Careers, spring of 2026. This is topic number 4, Introduction to Electrical Engineering Technology. So, similar to our first topic, there can be some confusion about what electrical engineering technology, or EET, is in relation to electrical engineering. Again, we should understand that an electrical engineering degree is typically a 4-year BS or Bachelor of Science degree. UMass and Western New England University both offer electrical engineering or EE degrees. Western New England University also offers various options to their EE degree. You should see Western New England University's catalog for more details. So, STIC offers, through the engineering transfer program, the first 2 years of a 4-year electrical engineering degree. It requires the students to take calculus and to take courses that are calculus-based. Once you get that, you could take and transfer to a place like University of Massachusetts or Western New England University. STIC also has a 2-year associate's degree in electrical engineering technology. But one should be aware that it's not the first 2 years of a 4-year EE degree. All the courses are algebra-based. There is also a 1-year certificate in electrical/robotics technology. That's the EROB.COC. There are area colleges that offer a 4-year electrical engineering technology degree. University of Hartford, for instance, they come to mind. But these programs emphasize hands-on practical skills instead of the theoretical emphasis of a normal BS-EE degree. The University of Hartford's program is actually a CEET, Computer Electronics Engineering Technology degree. It's a 4-year degree. So, in class we watched the first video, what is an EE? You should take and watch these videos, what is an EET and other EE topics. I'm going to continue on with the lecture. So, at Springfield Technical Community College, the Electrical Engineering Technology degree, the EET degree, in the first semester, you have, and you might notice that a lot of the classes are 2-credit classes with a 1-credit lab. So, there's EET 101. The title of that is PCs, Programming and Robots. There's a lab that goes with that. There's also EET 104 through 106. These are 1-credit modules. 104 is Health and Safety in Industry. 105 is Technical Diagrams for Automation. And 106, Developing Troubleshooting Skills. Those are all available only online. Then there's EET 110, Basic Electricity, or DC, and the lab that goes with it. EET 120, a Fluid Power course, and that has a lab built into it, but it's just one 3-credit course. Then there's English Composition and Tech Math, general education classes. If we go to semester 2 of the Electrical Engineering Technology program, we continue on with our basic fundamental theory of electricity. EET 111, Basic Electricity 2, is AC circuits, and there's a lab that goes with that. Then there's EET 130, Fundamentals of Motor Control, and a lab that goes with that. EET 135, Programmable Logic Controllers, or PLCs, and a lab that goes with that. EET 140, Fundamentals of Robotics, and a lab that goes with that. And then Technical Math, another general education. In semester 3, there's a 2-credit course, Solid State Electronics, and a lab. Digital Linear Integrated Circuits, and a lab. The second EET 235 is the second Programmable Logic Controllers course, and a lab that goes with that. Then there's EET 240, Robotics and Automated Systems, and a lab that goes with that, and Fundamentals of Oral Communications, and a General Education elective, more Gen Ed courses. Finally, in semester 4, the EET program, there's EET 250, Control Systems, which I teach, and a lab that goes with it. Then there's EET 155, Advanced Topics in Electrical Engineering. EET, that's probably should be 265, and EET 260, Microprocessor Applications, and a lab that goes with it, and Advanced Automation, and turns out there is a senior projects lab that goes with that, and then there's a general humanities elective and a general behavioral social science elective. The robotics technology certificate of completion is very similar. I'm not going to go over this in detail, but semester 1 looks the same as the other semester 1, and then semester 2 basically is the same as semester 2. Notice there's no gen ed in these. If I go back to the slide before this, which I apparently am not allowed to, turns out there's no gen ed either. So, with all that said, any of these programs that are involved with electrical engineering technology, you learn the basic DC concepts, and that there are circuit parameters. In any circuit, there'll be voltage, current, and resistance. Ohm's law is the ratio of the voltage to the resistance, tells you what the current will be, or I can figure out a voltage if I know the current and resistance, or I can figure out the resistance if I know the voltage and the current. Ohm's law has been around for many, many years and allows us to analyze circuits. The third bullet down, types of circuits. Turns out we can arrange components in series, in parallel, or combinations of those two. And we like to try to teach you how to, learn which one of those is which and be able to identify them and so forth. Then we talk about voltage sources, batteries, and power supplies. We look at making measurements in lab, voltage, current, resistance using digital multimeters. And we also talk about how we can solve these circuits through a computer simulation software program. So we now go back to the basics, the theory of atomic structure. This shows a Bohr's model of an atom, which shows electrons in orbit around a nucleus. The nucleus would contain neutrons and protons, and for many, many years we've used this model to take and try to understand the structure of our universe and the materials in it, the elements, and so forth. However, that's changed a little bit recently, but we'll get to that later on. Basic atomic components that give atoms their electrical properties are the electrons and protons. You might note the similarity of Bohr's model of atomic structure to that of the solar system, the electrons orbiting the nucleus like planets orbiting the sun. So these two diagrams show simple atoms, and these atoms are the fuel of stars, because usually what happens, a star forms when enough of these coalesce together. So on the left-hand side, you have the hydrogen atom, which is has one proton as a nucleus and one electron orbiting the nucleus. On the right-hand side is the helium atom, and again, now the nucleus is two neutrons and 2 protons and 2 electrons orbiting the nucleus. So hydrogen atoms fuse into helium atoms, and further fusing goes on to make heavier atoms and elements and so forth. That's really where everything has come from. And again, these are the two simplest atoms, hydrogen and helium. So I think I skipped over a slide real fast, hopefully not. Quantum mechanical model of an atom. I just mentioned that, the Bohr atom has been with us for a long time. Well, basically it's incorrect. And today we talk about a quantum mechanical view of atoms, and you see here that quantum theory describes an electron probability distribution, and this figure shows a distribution for the ground state of hydrogen. Notice the nucleus is in the center, but then there's a value R0, the radius away from the nucleus, that is most probable for electrons to be, but you see all the dots, and it turns out the electrons could be a lot of different places. So, I guess what happened, the slide I skipped over was the quantum microscope image of the hydrogen atom previously shown. So again, you can't go back to that, unfortunately, but we'll continue on. So here's a little more of the quantum mechanical model versus the Bohr model. And the quantum model you see on the right is there's these areas, regions of space where electron may be, and they're kind of weird looking. They're not these nice orbits in the Bohr model on the left, where there are orbits, distinct orbits, and nice circular orbits and so forth on the paths that the electrons travel according to the Bohr's model. Whereas in the notice they're labeled differently. There's shells on the left and they're orbitals on the right. How does this affect our understanding? How does this affect our understanding of electrical properties? Not really any way. It turns out that we can still talk about electrons as being a current and so forth. So the Bohr's model actually serves us well to understand electrical properties, but the quantum model gives rise to refining our understanding of atomic structure and materials and how they operate. And the middle, I'd say there, does this give rise to the possibility of room temperature superconductors in the future? And it might. The more we understand of the quantum nature of things, the more we might be able to manipulate stuff to do things we'd like to, like having superconductors. So here's an atomic periodic table of elements. This came from the chemistry field. Various naturally occurring and man-made elements have been organized into a periodic table of elements by scientists known as chemists. This has been around for a long time. Elements have atomic numbers and are organized by their properties. So what happens here is we might see 1A on the far left, hydrogen, lithium, sodium, potassium, and so forth. Those all have common characteristics. On the far right, we have 8, column 8, which is helium, neon, argon, krypton, xenon, and radon. And all those are gases, inert gases. Column 4A, carbon, silicon, germanium, and so forth. Tin, lead, silicon, and germanium, Si and Ge are semiconductors. Column 3A and 5A are important because we dope silicon and germanium with those elements to form N and P type semiconductors. If you go over to, 1B, column 1B, copper, silver, gold, those are all conductors. Of course, we use copper for our wire, silver and gold a little bit too expensive, but it turns out that how these atoms are organized by their atomic structure, the number of electrons in various orbits according to the Bohr model. So again, what can we learn from the periodic table? An element's physical and electrical characteristics are determined by its atomic structure. The periodic table is arranged by groups of elements with similar atomic structure. Elements in the same group or column have similar electrical properties and behave chemically in a similar fashion. So this shows, again, column 1. Now, there's something in the Bohr's model. We talk about valence electrons. So this shows a Bohr's model of the copper atom. And notice that the copper atom has 29 protons in a nucleus, and then there are 3 shells, and the maximum number of electrons that can be in those shells, according to the Bohr's model, is shown as 2, 8, and 18, which makes up 28. So there would have to be a 4th shell of 1 electron, and notice that the copper atom has a single electron in its valence band. As studied before, the first 3 shells are at capacity. This single valence electron is loosely bound to the copper atom and can be liberated from the atom through heat energy and many naturally occurring circumstances like electricity or charge. So what we come upon is categories of materials. So depending upon a material's electrical properties, it may be classified as one of the following: either a conductor, semiconductor, or insulator. And again, the material's behavior is extremely dependent upon the number of electrons in its outermost shell. That's the valence shell, again, by the Bohr's model. Also, we are not including superconductors here. So conductors typically have 1 valence electron. I'll show again. This is column 1B from the periodic table. What type of atomic structure makes a good conductor? You might see a copper atom, and a simplified diagram is that the copper atom has, again, a positive 1 at the center and a single minus at the outer. If I equalize the 28 other nucleus protons and the 28 other electrons. So elements of column 1B are good conductors. They're copper, silver, and gold. So semiconductors, conductors, and insulators. Best conductors have 1 valence electron, again, column 1B. Best insulators have 8 valence electrons, column 8. Best semiconductors have 4 valence electrons, column 4A. Those are all shown here. So copper wire, I've got a couple pictures here. The least expensive of the 3 elements just mentioned as conductors, copper is used to make wire, which is used to deliver electricity. You might note that early wire was made from iron. Copper was not, mined heavily and refined as much as it is today. There's a couple pictures of wire you can buy at Home Depot. Copper wire. Gold-plated connector examples. Here I show these electrical cable connectors are gold-plated. In theory, they're better conductors, but in reality, they resist corrosion better. That's why they're gold-plated. And the plating is very, very thin, only atoms thick. Here's some gold-plated connector examples of HDMI cables or audio cables. Does it really improve your signal and so forth? It's highly debatable. Probably not worth the cost of the gold plating. But it is good for, again, corrosion resistance. Stuff exposed to air will corrode. So electrical charge, most of us know about electrons and protons. The concept and characteristics of electrical charge, similar to magnetic poles. What do we say? Like repels and unlike attracts. So we should have 4 examples down below. Uncharged, there's no force on, say, these metal globes. If I have a metal globe that's positively charged and one that's negatively charged, they attract. If they're both positively charged, they repel. If they're both negatively charged, they repel also. So there is attraction and repulsion of electrical charges. If I talk about 2 oppositely charged surfaces, I show plus on the left and minus on the right here. By convention, historical convention, electric field lines are drawn as starting on the positive charge and terminating, that is the arrowhead, on the negative charge. We're kind of stuck with that over the course of time. Electrical charge units. There's something called the Coulomb, which takes and honors this guy Charles Coulomb, who lived a long time ago. On the right-hand side, you see his little bio there. So the Coulomb is a unit of charge, and Q, the number of electrons divided by 6.24 times 10 to the 18th electrons per Coulomb will give you the number of coulombs. So if I have 6.24 times 10 to the 18th electrons or protons, it is 1 Coulomb of charge. Today we can say that 6.24 exa-electrons is a Coulomb. The number of electrons that constitute a Coulomb comes from chemistry. So now we kind of switch gears to basic electrical parameters. And again, we mentioned before, those are voltage, current, resistance. So in any circuit, you end up having these parameters. Voltage is defined as the potential to do work per unit of charge. The unit of voltage is V. Now, there's an equation here that says voltage is W over Q, or W is work or energy, is given in joules. Q is charge and given in coulombs. Well, rather abstract equation and not of much use to us, because when do we talk about joules and coulombs and talk about volts? A more practical definition of voltage, and by the way, voltage is we honor this fellow named Volta, who lived a long time again also by his bio there. The more charge is separated, the larger the voltage value. Also, the more voltage that one measures, the more the potential for doing work. So in the next section, we will depict ways in which charge may be separated. Depending upon the method, one may produce small or large voltages. Charge is separated in the natural process of creating static electricity. Batteries are the first practical way to control the separation of charge. And again, I would point out that a common definition of voltage is that the higher the voltage, the more potential there is for it to do harm to you. So, I mean, that's another thing you can take into consideration. We talk about what voltage stands for. You're aware of some common voltages already. 120 volts AC tends to be what you have in your household, either 120 or 220 or 240 volts. Batteries are about 1.5 volts. Car batteries about 12 volts and so on. Current. Now, current is defined as the rate of flow of charge. So if we have a voltage, it turns out that if we have a circuit, we will get a flow of electrons. And again, according to the Bohr model of an atom. The equation here says I equals Q over T. So number of coulombs per second give you the charge or current in amperes. So 1 amp happens if I have 1 coulomb or 6.24 times 10 to the 18th electrons passing a given point per second. So what is a quantum view of electric current? Well, in the context of quantum mechanics, what is electric current flow? It is the flow of the probability of the presence of an electron. So one might think more of a cloud of electrons or a gas cloud of electrons moving. This also has some ramifications involving our concept of resistance. Hence the possibility of superconductors or the lack of resistance, which classically was the collision of electrons with atoms, which slowed down the flow of current. or resisted the flow of current. So here's a current example. I'm not going to go over this, but you can see that the example says we have 10 coulombs and it flows past a given point on a wire in 2 seconds. Well, that works out to be 5 amps. You want to maybe look at this example depending upon your prior experience or lack of prior experience about this topic. Now, that brings us to resistance, and I would point out to you figure 2-16 up there shows the symbol for a resistor, R. Resistance is defined as the opposition to current. The unit of resistance is the ohm, and it's symbolized by the Greek letter omega. The inverse of resistance is known as conductance, or G. So this equation shows that resistance and conductance are the reciprocal of one another. Conductance is a measure of how good a conductor something is. That is a physical thing. So the equation G is 1 over R, or R would be 1 over G. Conductance has been used, or rather conductance used to have units of mhos, which is ohm spelled backwards, but today has standardized units of Siemens or Simons. 1 ohm of resistance or 1 Simon of conductance exists if there is 1 amp of current in a material when 1 volt is applied across the material. So these are Greg Simon Ohm. He is famous for Ohm's law, and then Ernst Simons, again, lived many years ago. So that brings us to voltage and current sources. So here we show a battery. So batteries separate charge due to chemical reactions. So there is an electrolyte, and there's 2 different types of electrodes put into that electrolyte as shown here. It shows a porous separator, and it turns out it shows a positive electron on the right, electrode on the right, and a negative electrode on the left. So a chemical reaction occurs, and the electrons come from the positive electrode to the negative electrode, and they kind of mount up there, or amass there. The electrolyte is a solution that contains ions. So battery current capacity depends upon the physical size of the battery, and what materials are used give rise to what voltage you get. So here's something you're probably familiar with, typical batteries. You see a DC, AA, AAA cells from Duracell. They're all constructed from the same materials and have an output voltage of about 1.59 volts actually when unloaded. Today, other batteries may be made from a variety of materials. So here's a typical lithium-ion car battery. This is a car battery for a hybrid or electric vehicle. Consists of many batteries or cells wired together to generate high voltage, hundreds of volts. This is, I think, a Prius battery. So here we have some battery configurations. You probably, from your life experience, may have played with this. Certainly with a flashlight, you put batteries in series. So here's 2 arrangements. On the left, series connected batteries, and the voltage adds up. Each one adds to the next. Parallel connected battery, you put all the pluses to the pluses and the minuses to the minus, and what we get is the same voltage as one cell, but the possibility of much more current. So on the left-hand side, we'd have 5 times the battery of a cell, the voltage of a cell. And again, series cells yield higher voltage, while parallel cells yield a smaller voltage but greater possible amount of current. Other sources of voltage, you see the solar panels here. So solar cells, the sun's energy provides the means to separate charge. If you want to see more detail about this process, do a YouTube search. So you see 2 semiconductor layers there, N and P type, and a junction between the 2. And then you see light impinging on it. And what happens, you get a voltage across the top to the bottom contact. Turns out it's about 0.54 volts, I believe, for a solar cell. So you tend to put them in series and parallel to get more voltage. That brings us to basic AC concepts. So AC voltage are sine waves, and we use it for power distribution. All our electronic stuff needs DC, so we have to convert it back to DC. Capacitors and inductors are frequency selective or sensitive energy storage devices, as opposed to resistors, which are not frequency sensitive. Applications of C's and L's, or capacitors and inductors, resonant frequencies, oscillators, filters, the heart of wireless technology. Signals for wireless communications, high frequency sine waves, propagate through the air. So other sources of voltage. We see generators in this picture. So there's a cutaway view of a DC generator. Everyone that owns a car has a DC generator called an alternator in it. Mechanical energy is used to separate charge in a generator. This is due to Faraday's law. The generator effect of passing a wire or conductor through a magnetic field causes current to flow in that wire. So this is a generator. Here's a picture of sine wave generation. This picture, we've already done a 90-degree loop here, that the loop was parallel to the surface of the slide, I guess you'd say, and has gone through 90 degrees. Now it's perpendicular to the surface of the magnet, the north and south pole, and so the wire is moving through a magnetic field, which causes a current to flow in the wire. Notice the wire, as it moves, goes through a sinusoidal movement. That is the number of flux lines that pass through changes with time, so you get this sine wave. We go to the next slide. Now it's gone through another 90 degrees. You see the magnetic field is perpendicular to the north and south poles. Now the wire is perpendicular to those things, and it's not cutting through any flux lines, and therefore the voltage goes to zero. I go through another 90-degree turn. Now I have a negative voltage because the wire is moving through the flux lines opposite to what it was as it was moving upwards before towards the North Pole. Now it's going down towards the South Pole. And finally, if I go and do a final 90 degrees, I get back to where I started. I get my output waveform on the left. It's 0 to 360 degrees, correlated to the 360 degrees in a circle, and that is a sine wave. So the slip rings provide you with the sine wave output. In a DC generator, you don't have those slip rings. It turns out it gives you a DC coming out. Other sources of voltage are power supplies. You see these in the lab. And one of these, you plug the AC voltage, you get AC voltage from the wall outlet, and you get DC voltage coming out of the electronic power supply. It's more efficient to transmit AC power, but must be converted back to DC. As I said before, all electronics needs DC. Today, in some instances, it's been found that DC transmission of electricity is more efficient than AC transmission. That usually only happens at like 1,000,000 volts. So most of our grid is AC in nature, although there are some DC power grids being developed at this point in time. Voltage source symbols. These show symbols. If it's a battery, a DC source, you see the symbol under the DC source on the left with a voltage and a plus and minus indicated. If it's an AC voltage source, we put a sine wave in it, and we also have a symbol that tells us what the voltage is. These are the typical symbols used to represent simple voltage sources. Resistors. There's many different ways resistors are produced, manufactured. A is a carbon composition, B a metal film chip resistor, C is a chip resistor array, D is a resistor network, E is a resistor network surface mount technology, and F is a radio lead for PC board insertion. That would be a high-powered one. So all kinds of physical different implementations of resistors. Resistors tend to, the ones here, have a color code on them to indicate what the value is. This shows the internal construction of this resistor. The cutaway view of a tiny chip resistor on the right turns out to show you how that's built. So the resistors on the left were for through-hole technology, while the newer resistors on the right use surface mount technology. Here's a nice pretty picture. Resistors known as metal film resistors. They were very popular when through-hole technology was used to make printed circuit boards, PCBs. That's in the 1980s to 1990s. Note that a color code was used to indicate the value of resistance. So here's some more pictures, a typical construction of a thin film resistor. Resistor color code. I'm not going to go into this too much. You could do an internet search. You usually find a resistor color code calculator. The bands stand for the first, second, and third digit, and then percent tolerance, and then maybe other bands indicate other things. So here's a picture of the color code. I'll let you take a look at this. Here's some examples that tell you what the, they show you some examples and tell you how to figure out what the values are of the various resistors. And again, depending on your background, you may or may not be familiar with this, so I'll let you take and spend your time as you might on it. There's a reliability band, possibly a fifth band, used to indicate reliability resistor or failure rate. It's often a mil spec or military specification type of band. So here shows surface mount technology. Today's surface mount technology used to construct printed circuit boards. Surface mount resistors are shown by this picture, and notice they're labeled in different ways. We can also have variable resistors. Resistors may be designed to allow for a variable value. In lab, we might call these things trim pots. The pot standing for potentiometer. So you see little diagram A there. We have a wiper. The full value of the trim pot of potentiometer is from 1 to 2, but we can take and have a wiper which can divide that resistance up in terminal 3. We can take and have things called rheostats that only have 2 terminals and vary the resistance, or we can actually take and connect a potentiometer as a rheostat by taking one end and connecting it to the wiper. And the physical device is shown down below, figure 220. So typical variable resistors, these types of components are going the way of the dinosaur. They're being replaced by digital versions of potentiometers. Consider your TV remote control and the button touch-operated volume control. So now there's other components, thermistors and photoconductive cells. A thermistor is sensitive to heat. Its resistance varies with temperature. A photoconductive cell has a varying conductance with light intensity. So here you see the symbols for these. The thermistor has a T next to it with a variable resistance, and the photoconductive cell shows light going in. That would change its resistance. Here I show an Arduino with a couple modules with a temperature display. There's a variable resistor there. On the right-hand side is a proto board with a thermistor and a resistor. So what happens, I put red and black across that circuit, the series thermistor and the resistor. So that's 5 volts. Then the yellow wire is at the junction of the resistor and the thermistor. As a thermistor changes its resistance, the voltage at that junction changes. That goes into pin A0 on the Arduino board. The program takes and reads that voltage, digitizes it, and eventually the program displays the temperature as being 28.88 degrees Celsius on the display. Here are thermistors and photoconductive cells. You see that they have a lens or window to expose the device to light. These are typically found in heating appliances to detect the presence or absence of a flame, a safety integrated part of the system. So that brings us to an electric circuit. So here we see a graphical display, figure 228, of a battery, a lamp, and a conductor, a wire. On the right-hand side, figure 229, the schematic for that. Notice the battery is the battery schematic we saw before, and the lamp has a new way of drawing it. So this is an electric circuit. An electric circuit is usually a complete circuit, or it doesn't work. So we have switches. Everyone who's listening to me has gone into a room and thrown a switch to turn a light on. So typically switches are used to control the flow of current in a circuit. So the top circuit shows the switch is on, and we have a closed switch there in the schematic on the right, and so the light lights up. In the bottom schematic B, there's no current in the open circuit. Notice the schematic shows the switch open, and no complete circuit, hence no flow of current. In these circuits, I say note the direction of current flow. That's called conventional current, where the current goes from plus to minus. We know that now that we know about electrons, that's opposite of what really happens. The electrons go from the negative side of the battery to the positive side of the battery, opposite to the conventional current. We call that electron flow. Okay, so here's some more complex switches. I'm not going to go over this in detail, but you notice we can have switches with several positions, so we can control 2 lamps with 1 switch. We call this a single pole double throw switch. Many different types of switches, and I'm going to show them probably in the next slide. Yeah, so here we go. Single pole, single throw, single pole, double throw, double pole, single throw, double pole, double throw. Other switch symbols are normally open push button, normally closed push button. They have springs on those, and a single pole rotary 6-position switch. Most of those things have been replaced by electronic components. So again, switches may take on many different physical forms. Switches can wear out. Semiconductor switches don't wear out. They can fail, however, catastrophic failures, so they are preferred over these mechanical switches whenever or wherever possible. More switch details today. We have touchscreen displays. Then we have protective devices. We call these fuses. To protect electrical systems, we use fuses or circuit breakers. They are designed in a way so that if excessive current is drawn by a system, due to, say, a component failure, they will open up and stop the flow of current. Fuses cannot be reused. They destroy themselves when they are opened up. The circuit breakers down the bottom here can be reset and reused. How about wire conductors? Wires have existed for over 200 years. Recall the telegraph was invented in 1836. The early telephone system used iron wires, which weren't very good conductors. Today, most wire is made from copper or copper-coated and has insulation on it. In a circuit, a wire is considered to be a perfect conductor with zero resistance. Early resistors were constructed from various lengths of wire. This picture of New York City was in the late 1880s. There were many telephone electrical wires. What happened? They were eventually buried underground with the subway system. So it doesn't look like this at all anymore. Wire characteristics. Wires vary in diameter but conform to standard gauge sizes called the American wire gauge, or AWG. This seems backwards, but the larger the AWG number, the smaller or thinner the wire. Wire sizes are given in terms of cross-sectional area. This measurement is called a circular mil. So here's a AWG table, and actually you notice it goes from 0 to 40. 40 is real thin, thinner than human hair. 0 wire is at this point pretty thick. Then we added 2 zeros or double aught, 3 zeros, triple aught, or 4 zeros or quad aught, even bigger wires. And the area in circular mils is given by this equation. Area is equal to d squared. What about grounds? Ground is a reference point in the circuit, has a potential of 0 volts. Earth ground is commonly used by the utilities, the electrical, telecommunications, or cable, phones. Electronic equipment often uses a chassis ground, which may or may not be connected to earth ground. A car uses a chassis ground. Grounding is an important safety consideration. So here's some ground symbols. Grounds are a common point. So the circuit down below there shows that I use a ground symbol to connect or complete the circuit. That could be the chassis, could just be a common point. Here is a little bit practical knowledge for your residential outlet wiring. In electronics all the time we use red and black as positive and ground. Note that unlike electrical circuit conventions, red positive, black negative, or ground, in residential wiring the hot lead is black. It's totally opposite. And the neutral or ground lead is white in AC powering. One thing you might not notice here, if you take a look at the outlet has 2 slots. There's also the green wire, which is also ground. The 2 slots, the ground or white or neutral wire is connected to the wider slot. The hot is the one connected to the shorter slot. And you might also notice that the hot has like brass color, where the neutral or ground is kind of silver color for the outlets. So what about basic circuit measurements? Voltage, current, and resistance measurements are commonly required in dealing with electronic systems. At one time there were voltmeters, ammeters, and ohmmeters. Today these functions are all combined into a single instrument known as a VOM or multimeter, usually analog, or a digital multimeter, usually we call it a DMM. DMMs are typically used today. So here's some older meters. The one on the left is all but obsolete. The one on the right, the digital meter, today their cost is so low that it makes very little sense to purchase an analog meter if you can even find one. Typical meter symbols, a bar graph, digital, needle, and just a general symbol here. Popular software products like Electronic Workbench, EWB, Multisim, Circuit Maker, Circuit Designer, and Tinkercad all use these for circuit simulation. Something like this or similar symbols. So if I want to measure current, I have to take and interrupt the circuit. So here I show a battery with a resistor, alligator clips attaching a battery to the resistor. The circuit on the right is a schematic of that. If I want to take and measure the current, I have to take and undo one of the leads, open the circuit either between the resistor and the positive terminal, or between the resistor and negative terminal. That's shown to the right there in the schematic. And then I take and I put a meter in there. So this shows a battery, a resistor, and then 4.1 milliamps being read by this meter. And the schematic shows that on the right. Measuring current requires that the current in the circuit flows through the current meter. It's the only way I can measure current. Measuring voltage, I can measure voltage across things. I don't have to disconnect stuff. Measuring resistance, I have to take the component out of the circuit, make sure there's no power applied to it, and I can measure the resistance with a ohm meter. So here's some popular digital multimeters. Resolution of digital multimeters is kind of shown here. Present-day technology allows for accuracies in the range of thousandths of a percent. The typical test bench setup, simulating the circuit with Tinkercad will yield the same basic measurements. The typical proto board, you got to understand that what happens, the columns are connected together, they're separated in the middle, and then the things that run across the entire rows in the top and bottom are all connected together. Measuring circuit current, you got to again break the circuit. This is easier using Tinkercad. Measuring voltage, we go across. Measuring resistance, we have to take the component out of the circuit. So here's a bunch of symbols: battery, resistor, potentiometer, rheostat, lamp, grounds, all the switches, fuse, circuit breaker, voltmeter, ammeter, and ohm meter. So summary of measurements: measure voltage across components, measure current through components, measure resistance of a component without any supplied power. Basic electric concepts, we've talked about those. Then we're going to take a look at active devices, diodes, transistors, and transistors are either bipolar junction transistors, BJTs or FETs, field effect transistors, and MOSFETs or metal oxide silicon field effect transistors. Then we'll take a look at applications of semiconductors, rectifiers, switches, amplifiers, and oscillators. Then basic digital concepts, we'll take a look at logic gates and binary number systems, combinational logic, registers, adders, counters, and memory.